Okay, as promised, I'm going to try to give you a video of the lesson that I taught on Wednesday and Thursday from 8.2 called Integration by Parts. You can see before I got started here, I went back to how to integrate ln x over x. That's a U sub that you did last semester. That's the only time we have integrated anything with ln is if there was an x on bottom. So this could be u to any power, and the 1 over x dx then is the du. And we integrate u du and get 1/2 ln quantity squared plus c. There's a reason that I kind of warmed up with that because I wanted you to see how we actually integrate ln x when it's not a u sub. So getting into the lesson, it really starts off with us talking about products. And the two examples of products that you've already learned how to integrate is when the two products, and again, or not again, but these products are non-constant. This wouldn't be an issue if they didn't both have an x in them. And so I say in this first example we can simplify it because those two functions, square root of x and x plus 2, play very nicely together. And you can distribute, and then it becomes a simple integral that you just use the power rule for both terms. The next example of a product that you've done before is called a U sub, and we've done these, and this is still going to be, hands down, the most commonly used technique of integration in this class. U is x squared plus 1, du is 2x dx, we 1/2, and then ultimately this is what you integrate. Parts is an example of two functions multiplied together, and let's just say they don't play nicely together. They're not a U sub, and I came over here in class and made up what the problem would look like if it was a U sub. It would be x e to the x squared, where u would be x squared and du would be 2x dx. And so you could 1/2 and take care of that easily. So what do we do with x e to the x? And I've worked the problem here, but let's go down here and I'm going to show you how to develop it. If we take the derivative of the product u times v, and I apologize for the dead mathematicians that overused u, because this isn't a u sub problem. This is just u, the function, like f of x. So if we differentiate u times v using the product rule, we would get u dv plus v du. And then my instructions are to integrate both sides. If you integrate the derivative of u times v, you get u times v. So the left-hand side is uv, and I've distributed the integral through the sum, and so it's the integral of u dv plus the integral of v du. And then the last step in developing integration by parts is if you have the product of the integral u dv, and I'll explain how to split that up in just a minute, it equals uv, and then we've subtracted v du from both sides, and this is the objective right here. This is what you need to learn. You need to retain this. Some of my students in years past have called it voodoo, of, whatever, but uv minus the integral of v du. So let's come down here and do x e to the x, since I did it up there already done for you. And I'm going to move my dv up here alongside my u. So I'll explain better on what's u and what's dv, but for the most part, u is going to be x and dv is e to the x dx. So to get our du, we differentiate and we get dx. And to get our v, we take the antiderivative, and that would be e to the x. And so by our formula up here, uv is x e to the x minus, that's a big minus sign, the integral of v du, so the integral of e to the x dx, and our answer is x e to the x minus e to the x plus c. And if you don't believe me or you want to see how this works, you can always take the derivative of your answer and see that it gives you x e to the x. Okay? So I have some examples already done in the notes, but let me go over them with you the best I can. Again, we've got a product of two non-constant functions. We let u be x. We let dv be sine of 3x dx. We differentiate x. We anti-differentiate dv. And then we put it in the formula, uv minus the integral of v du. Notice that I'm not doing the u sub. That's just too many u's for one problem. You need to start learning that when you integrate a constant in front of x within a function, a composite function, that your u sub is always going to produce the reciprocal, hence the 1/3 here and the 1/9 in our final answer. And I didn't put a plus sign there. So there we go. Here's our uv, and here's the result of integrating v du. The next example ups that x in front to an x squared. And I'm still going to let u be x squared and dv be cosine. So here's my du and my v, and here's my uv. But look what happens when I get to my v du. I still have an x that I didn't have in the last two examples because they were x, and when you differentiate x, you get rid of the x. It goes to a constant. And we still have this pesky x right there. So you have to do integration by parts twice. And so I'm going to come over here, do another set of u and dv. So here's my original uv. Here's my new uv from over to the side right here. My other v du. Integrate, making sure you can see right here where I drew the arrow, where I distributed the negative through and integrated. So this power right here can be very telling. It can tell you that it's going to take integration by parts twice to get the v du down to a constant times a function. So it looks like, man, is she being mean with this x to the 6th. And the only reason that it appears that I'm being mean is that I want to show you this really cool method when you need to do multiple integration by parts and you just don't want to. You do what's called in the book the tabular method. Some people call it tic-tac-toe, but you start off with your x to the 6th and your cosine x dx right up here. And then the first thing you do is you differentiate the left-hand side until you get to 0. And then you know you've gone far enough. On the right-hand side, you integrate. And this should kind of make sense to you because when you set up parts, you've got your u and your dv, and you differentiate to get to du, and you anti-differentiate to get to v. However, on this, you keep anti-differentiating until you get opposite that 0. So our original uv comes from this x to the 6th right here and the sine of x that's on that diagonal. And notice that I have drawn a diagonal until I got to the end of the right-hand side. Those are going to be the products of every term. The only thing that this is missing is the SIGN that goes in between them. And so when you have your UV minus your integral of V du, that's this negative right here. That's the minus V du that comes in that second diagonal. And then when you do parts again, you've got minus a negative, which makes this be plus, and it goes on and on and on. So, for example, in this second term of 6x to the 5th cosine, I've got 6x to the 5th cosine, and I have two negatives, the one that results in the alternating signs and the one that comes from integrating sine. And so if you just can keep that all straight, you'll be able to get all your terms. Look at what's going on here in front of your trig functions. You've got the derivatives x to the 6th, 6x to the 5th, 30x to the 4th, until you get to the constant, and then your trig functions are alternating sine, cosine, and so on. As promised from up above when we integrated ln x over x dx, which was a u sub, now we're finally getting to integrating ln x. And this is the one exception. When ln x is the question and the x is not in the bottom to be the u sub, then it's an integration by parts problem, and u is ln x. Trust me, this works. So u is ln x, dv is dx, du is 1 over x dx, and v is x. So when you put these together, there's your uv. Here's your integral of v du, because when you multiply 1 over x times x, you just get dx. And then when you integrate dx, you get minus x plus c. It's pretty cool that it works that way. You have one question on your homework that is arctan. Whoops. And it sets up the same way. Your u is the arctan, and your dv is your dx. The way that that works is if you don't know how to integrate something, as in the case of ln and arctan, then there's no way it can be your dv, because the whole objective is that you have to integrate it. Okay? Hopefully that makes sense. And then here is the crazy problem. I think you have one like this for number 30. So notice that on e to the x and sine of x, neither one of these functions are ever going to go to a constant. E to the x is just going to stay e to the x, and sine is going to bump back and forth between sine and cosine. But we're still going to take off on the problem, doing integration by parts once. Here's our uv, and there's our integral of v du, which I really can't do because I've got another e to the x cosine of x. So you do parts again. U is e to the x, dv is cosine, du is e to the x dx, and v is sine. And so I've come down here, and I've written my original problem, and that's something you're going to have to do in this step. Here's my original uv. Here's my new uv from the parts the second time. And here's my integral minus the integral of v du. And look what these two have in common. Here on the right-hand side, I have a minus e to the x sine x, and I have one over here on the left-hand side. So when I loop that integral over here, and I call this a loop-de-loop, I have two integrals of e to the x sine x dx. I bring my two terms that don't have the integrals down, and my final answer is divided by 2, and there's your lesson. Good luck. I will see you tomorrow or Monday or Tuesday.